Hello, welcome to this third tutorial in the Midas tutorial series. In this tutorial we will be looking at the finite element analysis of a rigid jointed frame. This is again a statically determinate structure. So we'll show you the uh, results from the software, finite element software, how to model it, and also the correlation with the hand calculations. Now, just to give you a description of the frame, this is how it looks like. We have two pin supports. So this is not having any roller support. So you have pin supports at A and H, point H, and you have a pin connection at the top of this frame. So that's why this particular analysis becomes determinate, even though it has four unknowns, two horizontal reactions and two vertical reactions, which are unknowns. You have several point loads applied on the structure and also a uniformly distributed load applied on the left side of the pitched roof. And we can see we'll see how to model this structure step by step in Midas Gen and look at some of the important conclusions that we can derive from this type of an analysis. So basically the objective of this analysis is to calculate the reactions, to calculate the axial force diagram, the bending moment diagram, and the shear force diagram, because these are the results that are very important and also useful for designing the structure and performing the checks on the structure. So let's see how we can model it in Midas Gen. Okay, so here we have the blank screen of Midas Gen. We can start by clicking on new project, and that's the Midas Gen model view. So first of all, we start by defining the units. We can go to the status bar here and change the units to kilonewtons and meters, and then we set the analysis type to two-dimension analysis, which is model structure type XZ plane. So all the forces and all the elements will be in the XZ plane. Okay, then we start by modeling a node at the origin. So this time we will not use the structure wizard as we used in the previous videos or previous tutorials. We'll start by simple node by node generation of the elements. So we go to nodes, create nodes, and enter 000 and apply. So that's one node generated. We can display the number of this node if I click on node number here, so that node number is displayed, and click on the front view, so that's the node number 1. If you wish to increase the size of the font size of the node number, you can go to this display icon, display option, node number, and increase the font to say 11. Click OK. So that's more visible now. Now we will use this node to create the column on the left. Let's go back to the PDF to see what distances should be used. So we basically have a column AC with midpoint B, so it's 2.5 meters 2 times. We need to copy that element. So going back to the software, we use model elements and extrude option, just like we used in tutorial number 2 for the truss structure. Extrude and select or highlight this node. So you just click on this node to select it and define in the dz, dx divide dz, we enter only in the dz 2.5 meters and 2 times. So that will create a vertical element. Apply. Let's see in the top view. So that's the element generated. Let's go back to the PDF and see what are the next distances we need to enter. So we have a point D which is 4 meters to the right of point C and 2 meters above point C. So basically we have to enter a distance 4, 0, 2 for creating this particular element. So again we select this time node number 3 and enter. We delete everything here and we enter 4 comma 0 comma 2, and remember to enter only number of times as 1 and apply. So we have got this element now. Okay, now again select this node here. Let's see what distance we need to copy. That's 2 meter down and 3 meters 2 times in the x direction. So basically effectively we have 3 comma 0 comma 1 added 2 times. So here we entered 3 comma 0 comma 1 and that is 2 times and apply. Oops, sorry, I need to change the direction. So that is 3 comma 0 comma minus 1. Select the node again and apply because it's in the downward direction. Okay, now I select this particular node here and let's see what distance I need to move it. So 3 meters and 3 meters, so 2 times 3 meters in the downward direction. So that makes it 0 comma 0 comma minus 3 2 times and apply. Again click on the front view. So that's the skeleton of the structure generated. Now let's define some materials and sections quickly. So go to model, properties, material, add. So we'll be using user defined material again. So 2 e times 8, so 2 into 10 to the power 8 kilonewton per meter square, and that is material 1, and click OK. Close this, then go to model, properties, section, add. This time let us use the I section for the columns. So we select the standard British standard PS 493 and select the British standard section, which is universal column 305 by 305 by 158. Okay, you can select any section, doesn't matter. The section properties will not be will not matter in the analysis as long as the structure is determinate. So that's the I section. Click OK and close. So all the sections have now been entered. Now we will define the boundaries of supports. So we have pinned supports at both these nodes. So we go to model, boundaries, supports, and select node number 1 and node number 8 and assign them as pinned, which is dx and dz restraint. So no rotational restraint and no y direction restraint, and apply. So I'll close this. Now to see what information I've entered in this model, I can go to works tree and see that I've defined 2 supports. You can display and undisplay them. Okay, you have sections. You can go to properties to edit the sections. So all the editing and highlighting the model can be done from the works tree. Now if you observe this drawing here, you have a pin at the top at point D. So we need to pin any one of these elements at point D. So we use the feature of moment release or beam end release to release the moments at this point. So pin connection basically means that we are releasing the moments so that we are allowing some rotation at this point. So we go to model, boundaries, and select beam end release. Okay, and select so we want to pin only this node. So for this particular element we'll use fixed pinned so that this J end is pinned. How do you know that this is I or this is J? I mean, which end to fixed pin means it could have been, this one could have been fixed and this could have been pinned. So to know that which end is I or which end is J, we refer to the local axis for this element. And to display the local axis, we go to display element local axis and click OK. If you see the local axis X here, the red line, you will find that it's going from node number 3 to 4. So the general direction is always from I to J. So that means node number 3 is I, node number 4 is J. So which means that let me just switch to the line view by clicking here. Now it's more clear. So which means that I need to release the moments at J. So that's why I need to fix node number 3 and pin node number 4 or J point. And now I select this element and click apply. So you have a pin here, and that's how the moments are released, and you can now get a pin type behavior. So I close this dialog box now and switch to the front view. Now we have another problem here. If you notice carefully, if I rotate this model, make it say isometric, we have another problem in this particular case is if you see the local axis Y for all the elements, all the Y axis, you will find that for all the elements, all these elements here, you have Y axis pointing into the screen, whereas these elements here, you have y-axis pointing in the opposite direction. Now what it does is it's not a problem from the analysis point of view. It's absolutely no problem from the analysis point of view. But when you are seeing the results for the forces, because in our example we are required to calculate all the beam forces, all the moments, all the shear forces and axial forces. In that calculation, it becomes difficult to interpret the result, because let's say if you're looking after the moments of this element, then moments will always be displayed along about the y-axis, local y-axis. Let me just save this model, save it. Okay, so I was saying that the moments are displayed about the local y-axis. Now if you have, say, a hogging moment on these two members, for example, if you have a hogging moment here, that is a negative moment, then although the shape in the software and the hand calculations will match, but the sign of the moments, that is negative or positive, or you can say hogging or sagging, that is determined by the direction of the y-axis. So in this particular case, if both are having hogging moments, then you will find that the left column is giving you say a positive moment, then the right column will be giving you a negative moment, which is correct from the sign convention of the axis, but from the user point of view it might be confusing to interpret the results. So that's why it is always a good practice to align the axis, at least the say the y-axis, because the sign of the moments is crucial for designing the structure for negative or positive moments. So we select these members and we just change the local axis angle. So in this case, for these two elements or this column, we need to reverse or change it by 180 degrees. So we go to model, elements, change parameters, change element parameters, and select element local axis, select change and enter 180 degrees. Select both these elements. So I have used the select single option and just I have drawn a window from right to left, just touching these two elements, and click apply. And now you see that y-axis is reversed. Okay, so now the moments all will have the correct sign as per the hand calculations. So now I close this and we can start applying the loads on the structure. So for the loads, I will undisplay the local axis so that it's more clear while viewing the model. So click OK. Right, so let's go back to the drawing and see what loads have been applied on the structure. Okay, so we have 12 kilonewton and 8 kilonewton horizontal forces on the left column. So let us focus first on the horizontal forces, because there are a lot of forces on this structure. So 8, 5, 12 and 8. So we'll remember this and we'll apply this at the corresponding location. Okay, so first of all, let's name the load case. So we go to load, static load. Let's name it P and user defined add. Now we go to loads. For any point load, we use the nodal loads option. That's P, select the name as P, and we focus on the horizontal loads first. So enter 8 kilonewton in the positive X direction. Select node number 3 and apply. Then we select 12 kilonewtons. Let me check. I have a short memory. So 12 kilonewton, apply. Then we have 5 kilonewtons here, and we have 8 kilonewtons here, apply. Okay, so horizontal forces are applied. Let's focus on the vertical ones. So we have 15 kilonewton here, 15, 25, 35 and 20. So we click on this node, select this node, remove fx and enter fz. So that is minus, let me see again, minus 15, that's minus 15, apply. Then we have minus 25 here, minus because it's in the downward direction, 35 here, and I guess it was 20, yeah, 20 kilonewtons. Okay, so that's all the concentrated nodal forces applied. Now we will focus on this UDL, which is 12 kilonewton per meter. So let's see, we go to loads, element loads for applying this uniformly distributed load. Load case name is P, uniform loads type, and direction is global Z direction or vertically downwards. Now here, since you can see in the figure that sorry, the load is not applied on the entire length of this member. It has been applied on the only on the projected length of this member, so only on the X length of this member. So that means when we are applying it in the structure, we need to make sure that we have selected the projection option. So we'll select projection yes and apply minus 12 and select this member. So select single and select this and apply. So it will look like it has been applied along the entire length, not on the projected length, but actually internally, since we have selected it yes, so internally the calculation will contain only the projected length, not the entire length. So from the display point of view, it does look the other way around, but it is actually doing the projection. So close this and let's check by displaying the values. So right click on nodal loads and display. So these are all the nodal loads, and right click on element beam loads to display the element beam loads. Okay, so I'll undisplay this now and undisplay the nodes. We don't want the nodes now. Let's run the analysis. So I click on this button here and perform the analysis. So the analysis is done now. Let us look at the results one by one. So we'll start with the reactions first. Reaction forces moments. Choose values here and select decimal points 2 and click OK. So these are the reactions. We have 4.32, 64.07, 78.93 and minus 37.32. We'll look at the results from the hand calculations also. Let us see the software results first. Just to note here is we can see the deformed shape as well in the software. So since we don't require the deflection for this problem, so I'll just quickly browse through it how to see the displacements. Okay, so that's the click on the deformed shape here, deform, and we'll check real deformation and click OK. So these are the deformation in meters. Okay, so deformations depend upon the section's shape. So it will change if you change the section shapes or material properties, material elasticities. So this is the only property which will depend, this property as well as the stress property will depend on the uh, actual dimensions of the element. The other things like forces in a statically determinate structure will not depend on the member properties. So we go to results, forces, and this time beam diagrams. Select axial force first. We don't want the deformed shape, so I'll check off the deformed, and we want to see the results of axial forces at all the locations of the elements. So I'll select I and J, which are the two ends of an element, and click apply. So here you will see the values of the axial forces. You can zoom in or out using the mouse scroll button, scroll in or scroll out, and click to finish the zoom. So these are the values of the axial forces. To see the shear forces, you click on FZ. Again, how do you decide which shear force is FZ or axial force is FX? That is done by looking at the local axis, which we have already seen. So apply, that is the shear force diagram. So maximum shear force is here, 48 kilonewtons. Okay, then you have the moment My. So apply, that's the bending moment diagram for the structure. Okay, now we will look at the hand calculations and see how they correlate with the software. So I'll take you to the last few pages of this document. Just quickly explain to you the different ways of calculating the reactions. So for the reactions, it's just simple equations of equilibrium, equations of force equilibrium, like vertical forces should be 0 at a particular support, vertical forces should be 0 in the entire structure, horizontal forces should be 0, and moments can be 0 at the supports, pin supports, and also at the pin joint. So that gives you the reactions, all the 4 reactions. Then to calculate the forces, we just take free body diagrams for each member and calculate the forces in this manner. So we have free body diagrams for each member, and we define the bending, we calculate the bending moment and shear force at different locations. For shear forces, we resolve the vertical component of the free body diagrams using simple geometry rules to get axial force and shear force. And then finally we get this kind of diagrams, which are very similar to what we obtained from our analysis, finite element analysis. That means the finite element analysis is in correlation with the hand calculation, as you can see here. Let's just zoom in. That's the Midas result, and that's the hand calculation result. Okay, so this concludes the session today for the rigid jointed frames. To know more about the other types of examples, simple examples on Midas Gen, stay tuned to the Midas UK YouTube page, and especially to the Midas Gen tutorials channel, which specifically focuses on this type of examples. That's it for now, and thank you very much.